In this video, I will discuss construction of character table using rotational vector components as basis. The most common vector associated with rotational motion of a particle is the angular momentum vector L, which is equal to R cross P, where R is the position vector of the particle and P is its linear momentum vector. To generalize the concept, we take an arbitrary vector, say R, which is expressible in the form of a cross product like this, cross product of two vectors, say V1 into V2. Let R be a general vector expressible as a cross product of two vectors V1 and V2, where V1 is x1 I vector plus y1 j vector plus k vector z1. Z1 should be written on this side. Anyway, x1 I vector, y1 j vector and z1 k vector is v1. And let v2 be x2 I vector plus y2 j vector plus z2 k vector. Thus x1, y1, z1 are the Cartesian components of v1, x2, y2, z2 are the Cartesian components of v2. Then how is R obtained? R, the cross product of these two vectors, is obtained by expanding a determinant like this: I vector, j vector, k vector, then components of v1, that is x1, y1, z1, and x2, y2, z2. If you expand this determinant, you will get expression for R. And what is that? By expanding, we will get I times y1 z2 minus y2 z1, y1 z2 minus y2 z1 plus j vector multiplied by x2 z1 minus x1 z2 plus k vector multiplied by x1 y2 minus x2 y1. This is obtained by simply following the rule for expansion of determinant. Then these are the Cartesian components of R. We write them as follows: Rx, that is the x component of R, is this: y1 z2 minus y2 z1. Ry is x2 z1 minus x1 z2, and rz is x1 y2 minus x2 y1. Now, if we apply the symmetry operators of C4V on these components separately, let us examine what happens. What happens if C4 operator is applied on Rx? What is the result? For a point group C4V, the coordinate system is like this. This is the x-axis, this is the y-axis, and the z-axis is the fourfold axis of symmetry perpendicular to the plane of the paper. the sigma v planes, sigma v1 is the xz plane, sigma v2 is the yz plane, this is sigma v2, the yz plane, sigma d1 plane is like this, and sigma d2 is like this. I explained these in my earlier two videos. Now what happens if C4 is applied on Rx? This means C4 applied to y1 z2 minus y2 z1. What happens? Y comes to minus x by C4 and z remains unchanged. Therefore we will get minus x1. From y1 we get minus x1, z2 remains unchanged, minus, from y2 we get minus x2, z1 remains unchanged. And what is the result? The result is x2 z1 minus x1 z2. x2 z1 minus x1 z2 is ry. So from Rx we get Ry. Thus Rx and Ry are symmetry partners under the action of C4. So let us apply the same operator on the partner function Ry. What happens? Ry is this, x2 z1 minus x1 z2. X on transformation becomes, x on rotation becomes y. Therefore x2 becomes y2. z1 remains unchanged. I am taking ry from here. z1 remains unchanged, minus x1 becomes y1, and z2 remains unchanged. What is this? y2 z1 minus y1 z2 is minus rx. We get minus rx. Thus Rx and Ry are transforming together. From Ry we get Rx, and from Rx we get Ry. Let us next apply, say, sigma d1 on Rx. What happens? Sigma d1 on Rx. By sigma d1 x becomes y and y becomes x. Therefore, if Rx is this, then y becomes x. Therefore, this function becomes x1 z2. y1 becomes x1. So this becomes x1 z2 because z remains unchanged. Minus y2 becomes x2. z1 remains unchanged. And what is that? x1 z2 minus x2 z1. This is minus ry. From Rx we get minus ry by sigma d1. And sigma d1 operating on ry will give what? Ry is this, x2 z1 minus x1. So x2 becomes y2 by sigma d1. X becomes y. So x2 becomes y2, z1 remains unchanged, minus x1 becomes y1, z2 remains unchanged. And what is that? y2 z1 minus, this is minus rx. This is minus rx. Thus we see that Rx and Ry are transforming together. If we complete the list, we will find that Rz never appears here. Only Rx and Ry come together. Therefore, we have to write these results as a linear combination of two functions. If we take Rx, Ry, Rz as the whole basis set, then we see here that there is a partition. These two functions transform separately, and Rz transforms independently of Rx and Ry. These two will form basis of a two-dimensional irreducible representation of C4V. And we have to write these results as a linear combination of these two functions. Ry should be written as 0Rx plus 1Ry. This should be written as minus 1Rx plus 0Ry. And so from these two, as I explained earlier, the matrix for C4 will be these coefficients taken row-wise, 0, 1, minus 1, 0, and the trace is 0. Similarly, if we construct the matrix for sigma D1, what will be the matrix form? Sigma D1, we have taken Rx first and then Ry. So this should be written as 0Rx plus minus 1 into Ry. And this should be written as minus 1Rx plus 0Ry. And so matrix for sigma D1 operator will be 0, minus 1, 0, and trace will be 0. In this way, we can calculate traces of all the operators using these two functions and as basis. And therefore, we get a two-dimensional irreducible representation because these two cannot be separated from one another by any of the symmetry operators. And what are the characters of that irreducible representation? If I write in the usual way, character, then the operator E, operator 2C4, C2, 2 sigma D, 2 sigma V, basis is Rx, Ry together. And what are the characters? C4 has given character 0, sigma D1 has sigma D2 also will give the same character because sigma D1 and sigma D2 are in the same class. Sigma V we have not calculated here, but the same procedure will give a zero character for sigma V1, sigma V or sigma D also. Actually this is written earlier than this. This is the convention, first sigma V, then sigma D. C2 will give a character of minus 2 and E will give a character of 2 because there are two basis functions. Identity matrix for representing E will have dimension 2 will be of size 2 by 2. Actually identity matrix will be like this, 0, 1, 1, 0 and trace will be 2. Character will be 2. Now let us compare this set of characters with the characters that we obtained earlier. This is the set of characters. This is the set of characters that we obtained. Actually, these are 4 irreducible representations that we obtained using linear and quadratic functions of Cartesian coordinates. This 1, 1, 1, the totally symmetric one was obtained using z as basis or z square as basis and so on. This one was obtained using xy as basis or yz zx as basis. And here we see this set of characters is the same as this one, gamma 2. So we need not write it further. We only extend the basis set. The basis set here is Rx, Ry. So this irreducible representation has another possible basis set, Rx, Ry. Now let us calculate the characters for Rz. Characters for Rz. what happens if we apply C4 on RZ? C4 on RZ means C4 on RZ. What is RZ? RZ is x1, y2 minus x2, y1. RZ is x1, y2 minus x2, y1. So what will be the result? C4, x becomes y, so x1 becomes y1, and y becomes minus x. Y becomes minus x, so y2 becomes minus x2. Here x becomes y, so x2 gives y2, and y1 becomes minus x1. Thus we get x1 y2 minus x2 y1, which is the same function back, that is RZ itself. C4RZ gives RZ, C4RZ gives RZ, so C4 has character 1. C4 has character 1 like this. Let us wait. Let us apply sigma V1 operator on RZ. Sigma V1, RZ is this one, sigma V1 is this plane, this XZ plane. This is sigma V1. Z-axis is perpendicular to this plane, and XZ plane is a vertical plane containing the x-axis. Therefore, x remains unchanged and y is transformed to minus y. So from here we will get x1 into minus y2, and from here we will get x2, which remains unchanged, and y1 becomes minus y1. So this is x2 y1 minus x1 y2, and this is the negative of this function. This is minus RZ. So sigma V1 gives a character minus 1. C4 gives a character 1, but sigma V gives a character minus 1. Now look here. C4 gives a character 1, like this one or this one. C4 character gives character 1, like this case. Here character is 1, and here character is minus 1. Sigma V1 gives a character minus 1. So therefore, we have a new representation. Sigma V1 gives character minus 1. C4 gives character 1. So E will give a character 1 because our basis is RZ, one-dimensional representation. So character of E will be 1. E leaves RZ unchanged, so we get 1. And C4 gives 1, as we have got written here. Sigma V gives minus 1, we have written here. Sigma D, we will let us see what sigma D gives. Sigma D1 on RZ. What is the result? By sigma D1, this is sigma D1, x becomes y and y becomes x. Therefore, from this we get y1 x2 minus y2 x1 from this on sigma D. And what is this? X1 y2 is negative here, and x2 y1 is positive here. So this is negative of RZ. So character will be minus 1. So sigma D1 will give a character minus 1. So altogether a different representation. If you calculate C2 transforms, so x to minus x and y to minus y by C2. Therefore, x into y will remain unchanged. This also will remain unchanged. Therefore, C2 operation leaves the function RZ unchanged. We get character 1. we get 1, 1, 1, minus 1, minus 1. This is a new set of characters different from the earlier 4. So we have to use a new name here, call it gamma 5. Thus we get a total of 5 irreducible representations using linear and quadratic functions of coordinates and also the rotational vector components Rx, Ry and Rz. Now the question is, are there more irreducible representations for C4V? The procedure that we have adopted cannot give an answer to this. The final answer comes from a result of the Great Orthogonality Theorem. One result is that the number of possible irreducible representations is equal to the number of conjugate classes in the point group. Here the number of conjugate classes is 1, 2, 3, 4 and 5. And we have got 5 irreducible representations. Therefore, this is a complete list of irreducible representations. The basis set is not complete because you may extend the basis. You may find out other basis sets, basis functions. For example, you may take cubic functions of coordinates and you will find that some cubic functions transform like any of these irreducible representations. No more irreducible representation will be found. This is what one of the GOT tells us. So we have learned how to construct character tables starting from basis sets without taking much help from the Great Orthogonality Theorem. However, that theorem is very fundamental and useful, and we will arrive at that theorem by analyzing the matrices and characters that we have obtained in this point group. That will be discussed in some other video.